Hello, everybody. Welcome to our climate change lecture. Before we get started, I just wanted to address some of your exit tickets. The exit tickets demand more Chester, so here is the Chester kitty. He's currently a little peeved with me because his Chimkin is running low, and there's only kibble in his bowl and no Chimkin. And I don't know if you know this, but a cat can't survive on kibble alone. They need more Chimkin. So, um, that's what's going on at our house. He is still very snuggly. But let's get started talking about climate change. So, as you know, climate change is not going to be on your AP exam, but as a climate scientist, I would be remiss if I let you get out of APES without talking about climate change. So here we are, talking about climate change. So what do you think about when you hear the words climate change? Maybe you think about some glaciers. Maybe you think about some bleached coral. Maybe some wildfires. Or some CO2 emissions. Or maybe some desertification or deforestation or polar bears. A lot of people think of polar bears. Or maybe even permafrost. If you are like me, you might think of permafrost. So those are all things that people commonly think about when they think about climate change. All of those things associated with climate change. So if you're thinking of those things, you're on the right track. I just want you to be a little bit more well-informed about it, and so you can be more conversational with it as you go out into the big wide world. So we have 5 major questions that we are going to answer over the next 2 class periods. So today we are focusing on the first 3. What is climate change? How do we know it's changing? And how do we know that it's us? Okay. And then the last 2 questions that we're going to deal with on Monday are what are major impacts of climate change and what can we do about climate change? So, starting out with what is global climate change? A definition would be changes in average weather that occurs in an area over a period of years or decades. So, remember the difference between weather and climate. I hope you remember. I know it's been months, but remember that weather is local and climate is regional or global, and weather is short term and climate is long term. Okay, so I don't think you guys have seen this before, but I wanted to show you this diagram because it helps me when I think about the greenhouse effect. So this is Earth's energy budget. So we need energy coming in to equal energy going out in order for our budget to be balanced. So with the energy that's coming in, about 30% of it gets reflected back out into space, like before it gets absorbed by the atmosphere. So 6% gets reflected by the atmosphere, 20% reflected by clouds, and 4% reflected by Earth's surface. I think Chester has had enough climate change. So that's 30% off the bat that gets reflected by clouds or Earth's surface. Remember the term albedo, which is the reflectiveness of Earth's surface. And then 19% of it gets absorbed by the atmosphere and by clouds, and then gets re-radiated back out into space. And then another 51% of it gets absorbed by land and oceans, and then eventually will be re-radiated back out into space. So we want this budget to be balanced, 100% in, 100% out. But if we start trapping more energy in our atmosphere than is being released back into the atmosphere, you start seeing warming. Or if we start preventing energy from coming into the atmosphere, reflecting it before it can be absorbed, you would see cooling. So you actually saw this, the mini ice age year, which I think we talked about in class, where there was a volcanic eruption. It was called the year without a summer. It's the albedo and the reflectivity in Earth's atmosphere increased so much that we saw a year that it didn't effectively really turn into like a warm summer because the reflectiveness was so high. So the goal is to keep this balanced, but sometimes the balance gets wonky. Okay, so thinking about atmospheres, if we compare and contrast the Earth to the moon, so our Earth is nice and warm and hospitable, and the moon is pretty cold, right? You see lots of impact craters on the moon because there's not a ton of atmosphere to like break down things, so or to change the landscape. So there's not a lot of plate tectonic movement happening. I say not a lot. There's no plate tectonic movement happening, and pretty much everything that hits the moon you can see. So there's no atmosphere. It's very, very cold. Compare that to our other neighbor, Venus. So Venus has a super thick atmosphere, and it's very, very warm on Venus, and it's much warmer than what would be hospitable for life here. So we are kind of in that Goldilocks zone where our atmosphere is just thick enough that it keeps us warm, but it's not so thick that it makes our home too warm. Just remember the atmosphere keeps us warm. Remember the layers of the atmosphere: the troposphere, stratosphere, mesosphere, thermosphere. That the ozone layer is in the stratosphere. So we live down here in the troposphere. Okay, so think about a greenhouse in the dead of winter. So it could be like very, very cold outside, but you walk into a greenhouse and it's warm and it's sunny and there's green life growing. That's kind of what our atmosphere does for us, and that's what the greenhouse effect is. So it keeps us warm out in cold, cold space because it traps the sun's energy. It traps it inside, just like a greenhouse traps the sun's energy inside and keeps it warm. The atmosphere does the same thing for us. Greenhouse gases are gases that contribute to the greenhouse effect by absorbing infrared radiation. So they can hold that sunlight and they can trap that energy. Examples are CO2, methane, nitrous oxide, hydrofluorocarbons, perfluorocarbons, sulfur, hexafluoride. All are greenhouse gases that are famous. If you look at the ones down here, this says high greenhouse warming potential gases. Sorry. Those are your HFCs, your PFCs, and your sulfur hexafluoride. So they have a high warming potential, but they're not as abundant in the atmosphere as some of our other ones. So CO2 is pretty abundant in the atmosphere, and it has a greenhouse warming potential of 1, whereas methane has a higher warming potential, which we've talked about, but it's not as abundant in the atmosphere as CO2. Water vapor is actually the most abundant greenhouse gas in the atmosphere. It only stays in the atmosphere for a few days and has low warming potential. However, increased global temperatures lead more evaporation of water, which leads to more water vapor in the atmosphere, which is a feedback loop, positive feedback loop. So, what happens when we increase the concentration of greenhouse gases in our atmosphere? Does it get warmer? Does it get cooler? I hope by now you know that it gets warmer if you increase greenhouse gas. Okay, so part 2. I think I'm actually going to make a second video.